Okay, well, we're going to go ahead and get started. So you guys have an exam, a take-home exam. I'm not really sure how we're going to do a collection of work right now. I haven't figured that out. I guess there's only a few people in your class, so I might be able to do it by Blackboard scanning. I'll figure something out, so don't worry about that right now. We're still figuring things out on this end. The lab, what we'll do for lab, we won't do it tonight, but I'm going to send some information to you via Blackboard. There is some software we'll use. I'll tell you about that at the end of the session today. And we'll do the labs by remote using some simulation software. So I'll have something to say about that towards the end of the video. I'm recording each of these, and as I said, I'm going to post them to Blackboard, and you will have access to it. I put up a link right before this session. You don't really need it, but I put a topic sheet up in case you want to kind of follow along with what I'm doing here. But it'll be all available to you. So main thing you want to do is just take notes. And I think that's all I want to say to get started. I want to try, and I'm going to try something here to share a screen. I haven't tried this before, but there was a video I showed in class of Faraday's law. So I'm going to try to show that again. Hopefully I don't disconnect us or anything like that. I haven't used that feature of the software, so this will be my first time trying to share a screen. But I want to show that video again, and then I'll talk about the subject tonight, which is Introduction to AC Circuits. So let me see if I can share that video. I'll let that play, and then I'll come back and we'll get started. We'll see if this is going to work for me.
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. If I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also.
Okay, can you guys see me now? Okay, great. I guess I did that right. All right, so I want to talk about AC circuits. Up until this point, we've been dealing with a voltage and current that's been constant if I were to draw a graph of the voltage or current in a DC circuit, it's kind of boring. If this is voltage or current, V or I, and this is time, in the circuits we've been working on, basically this is what you have. It's constant. So DC, direct current, means that the direction of current doesn't change, the polarity of the voltage doesn't change over time. It remains constant, or direct current. Now we're going to talk about this other type of voltage and current called AC current, alternating current. And the reason I played that video for you is because the thing that creates the alternating current, the generator, is based on Faraday's law. That was a demonstration of Faraday's law in the video. I wrote it out on the board. I think in math, I gave in the other class last week, I gave you the math equation for it. But Faraday basically says if you want to induce or create a alternating voltage, which can cause an alternating current, you got to have three things. You got to have a conductor or a coil. You got to have a magnetic field, and there's got to be movement between the coil and the magnetic field. There's got to be some kind of motion. In the video, he took a loop and a magnet. The first coil had one loop. He moved the magnet in and out of the coil, and then he increased the number of turns and the number of loops in the coil to demonstrate the more turns I have on the coil, the more voltage I can get out. But the interesting thing is that if you notice, when he moved the magnet in and out of the coil, the meter, was measuring current and not voltage, but depending on which way he moved the magnet, the needle would deflect one way when he moved it in. When he pulled it back, it would deflect the other way. So if he were to continue to move it in and out of the coil, what you get is you have the needle or the meter moving back and forth, alternating back and forth to mimic the voltage and current. The voltage constantly changes and the current constantly changes direction. When you have that kind of voltage or current, it's called an alternating current. And that's what I want to talk about, and that's what we'll spend the rest of the semester talking about. So it's based on Faraday's law, and I know in class we talked about generator action, and we talked about the rail gun. I know we talked about the rail gun, but we talked about motor action, I'm sorry, but not generator action. Basically, what I mean by generator action is Faraday's law. If I have the three components I just erased, I can basically generate a voltage whose polarity constantly changes, which generates a current whose direction constantly changes. And so I want to talk about that. The machine that does that is called a generator. So I could have a magnet and a coil like he had in the video, and I can constantly move that magnet across the coil, or I can move the coil across the magnet. It doesn't matter which one I move. There's just got to be relative movement between the two. But either way, I can create a voltage and current that alternates back and forth. But that's not too efficient. If I had something like this, a conductor, and I had that near a magnet, north and south pole, the magnetic field that we talked about in class. If I move that wire or that conductor across that magnet, I can generate voltage that alternates back and forth. But as I said, that's not efficient. What we do is we make something called a generator. So I want to talk about a basic generator. So a basic generator, you would need a magnetic field. So I can get two fixed magnets with north and south pole. And I can draw, if you remember the terminology when we talk about magnetism, this would represent the magnetic flux. The flux has direction from north to south, flows from the north pole to the south pole. So if I have this magnetic field, and I take a piece of wire, but not a straight piece of wire. I have a wire that I bend into a loop like this. I bend that into a loop like that. Then what I can do is I can put a shaft on this thing. And once I put a shaft on this, I got a lot of different ways I can turn this. The thing is, according to Faraday, I got the magnetic field, I got a conductor. I can actually get this thing to produce electricity that alternates back and forth if I move that coil inside the magnetic field. So once you put the shaft on here, you can turn that. I might put a wheel on here, put a pulley on it like you have in your car. In your car engine can turn that. Maybe I put a blade or some kind of propeller here or a turbine here. Water can fall over the turbine to turn this, or you can stick this up in the air and the wind can spin this. Some kind of way we got to get this thing to move. And when I have this thing moving inside the magnetic field, basically I have what Faraday says we need to create a voltage, which then can cause a current to flow, and that current will be an alternating current and alternating voltage. Now there is one issue with this, one problem, that if I spin this some kind of way, let's say I connect up a circuit to this, maybe this is a light bulb, and I connect that up, the light bulb up to the coil. As I spin this, these wires are going to twist. So the way around that is they make something called slip rings. Slip rings. And the slip ring, the way to think about a slip ring is, imagine I have a copper pipe. So I got a copper pipe or a metal pipe, and that pipe is sitting up on the edge like this. So I just take the pipe and I set the pipe up like this, and I get a hacksaw and I cut this off. I cut a little piece off of the pipe, so I make it a lot shorter. So that's like a big paper towel roll made out of metal. I cut it off and get a little piece of it. If I set that up, what you have is a ring of copper like that. And then what you can do is take maybe a hacksaw, metal saw, and cut that ring in half like that. And now you got two half rings of copper. And then what they'll do is they'll take this half ring and put it on that top conductor, and this half ring and put it on the bottom conductor. If you were looking at this way, with the slip rings on it, this conductor right here would be here, and this edge of the conductor would be here. So then what you can do is you can take another piece of metal, just kind of put that piece of metal against that slip ring like that, and then do the same thing on the bottom, put another piece of metal on the slip ring like that. And then they have these springs, a metal spring forcing this way, and a spring forcing this up that way. So if you can follow the diagram, what you can do now, if I have these slip rings on the end of there, what I can do is connect my circuit up like this. So my light bulb is now connected to these are called brushes. And basically this thing can turn 360 degrees and still maintain electrical contact. So that's kind of the basic construction of this is an AC generator. Now you don't have to really, I don't care if you write this down, and I'm not concerned about the slip rings, but this is a basic generator. A basic generator. Based on Faraday's law, I have a coil moving inside of a magnetic field. It's going to induce or create a voltage, and that voltage is going to vary back and forth. It's going to cause a current to alternate back and forth, and I'll show you a picture of that in just a second, of what that looks like. Now, if you remember the lecture, we talked about motor action. We talked about the rail gun. We talked about motor action. This basically is the same machine. What we had last week when we talked about motor action, we had, if you think about it, we had some magnets. We had a coil that we put inside of a magnetic field. But what we did is we hooked up a battery here. And when we hooked up a battery here, current flow through the conductors, and we talked about strong and weak magnetic fields or weak fields. It actually causes this thing to rotate. So if I put in electrical energy, this thing will rotate. I have a shaft over here. I can actually do work with that rotating shaft. That's called a motor. If I'm putting in electrical energy, I get out mechanical energy. I got a motor, but what I've shown you here was the opposite. We actually, some kind of way, we spin the shaft in the magnetic field. So my input is not electrical energy. My input is mechanical energy, and I get out electricity. And that electricity is of the form that we call alternating voltage, alternating current. Now, I don't know if you guys can see this on the camera, and I don't know if I brought this in class. I can't remember if I showed you this in class last time or not, but if I did, I'll show it to you again. But what this is I have basically this thing. I have inside of here, I don't know if the camera can focus in on that or not, but I'll explain it to you. I got a handle on here, and this handle is basically connected to this shaft. And there's a motor out of a toy, and inside that motor you have magnets and you have a coil, and that coil is connected to this handle. And on the end of this, I don't know if you can see it or not in the camera, because I can't see how well it focuses. I'll try to get close so you can see that. But it's clear, so you can see that there's a motor and a gear in there. And if I turn this, there's a light bulb right there. If I turn this, rotate this, it'll generate electricity, and you'll see the light bulb light up. So I'll turn this, and you should see the light bulb lighting up. Now, there's also two connectors here that connect to the light bulb and to the motor. So just a second ago, I was turning this, and you saw the light bulb light up. So I was using this as a generator. Well, what will happen if I put in electricity instead of putting in mechanical energy? So there's two terminals here that I can connect up. I'm going to unloosen the light bulb, and I got a battery here. I don't know how well you can see this, but I got a 9-volt battery, and I got a wire, a clip. What I'm going to do is connect up the clip to the generator, output of the generator, and see what happens. No, I'm good. Yeah, thanks, Wayne. All right, thank you. Okay, so I have the generator, and I have it hooked up, the output. I got the battery. It's kind of hard to see because I'm going to try to hold it at the same time while you watch it. And if I touch this, what you'll see, you'll notice that the handle moves. So in this case, I'm putting in electrical energy. This is going to spin because of the motor action that we discussed last week. I put in electrical energy, I get mechanical energy. When I spin the shaft, I put in mechanical energy, I get out electrical energy. So basically, a motor and a generator are the same machine. In the most basic sense of the word, a motor is just a generator flipped backwards and vice versa. So we talked about motor action last week. We'll talk about the generator this week. This is a basic construction of the generator. But what I'm really interested in is, what does the voltage or current look like that's produced by this machine, this rotating machine? Now, I showed you at the beginning DC, voltage or current, V or I. DC over time is constant. It doesn't change in magnitude. It doesn't change in direction. It's constant. It's pretty boring. But if I could look at the voltage produced or the current produced by this rotating machine, it would look quite different. It will look like this. I got to make the graph a little different. So this can be the polarity of the voltage or the direction of the current. For now, I'll show current, but it can be V. And what happens is, as this thing rotates around 360 degrees, depending on the position of the coil in the magnetic field, it'll start out, say, at a low value, and it'll go up to a high value like that. It'll peak at a certain value, and then as this goes around 360 degrees, it gets at 90 degrees in the coil. When it reaches 180 degrees, the current or voltage goes to zero. As it goes around the full 360 degrees around one rotation, it comes back up like this. So DC is constant. Direct current doesn't change in direction or magnitude. But when I have a current or when I have a voltage produced by this rotating machine, it looks like this. It changes in both magnitude, and the fact that this part of the graph is below here where the negative values are doesn't mean I have a negative current. What it means is the current has changed direction. So for this part, this is called a cycle. This is one cycle of current from there to there. And for that one cycle, current has started at zero, went to a maximum value, went back to zero in one direction. And then as this coil continues around the 360 degrees, the current actually changes direction, or the voltage changes polarity, and it goes back up to a maximum value, back down to zero, and as it goes around. This represents one revolution of that coil in the magnetic field. And as it spins around, it creates a wave that looks like this. And you call that a sine wave. I'm sure you're familiar with that from your math class. But the point is that this type of voltage, the type of voltage or current created by a generator, looks like this. There's only a couple ways we can generate voltage, or we can get voltage or current. One way is, of course, we've been dealing with batteries all semester. You can have a battery. Another way is you can have like a solar photo cell, solar cell. You can use something called a function generator, which if you were here in lab, we would use function generator. But most of the time we create AC that we want to distribute power, it's going to be a generator. In your car, you have a generator, and in your house, that AC voltage provided to you at a residence or a business is created by a generator. Now, you might wonder, why do we need DC and AC? Why do we have two types of voltage or current? And it turns out there's a couple answers to that question, but the main thing is this. It turns out that it's much more efficient to transmit power in the form of AC than it is in DC. Actually, years ago, Thomas Edison, the light bulb dude, he had parts of the country wired up with DC. And it turns out that DC, the more wire you have to push a DC current through, the more energy loss there is. So it's very inefficient. You guys might know the name Nikola Tesla. There's a car named after Tesla. You may know a little bit about some of his inventions, but one of the things, he's the father of AC. He's been known to be the father of AC. And without going into too much technical detail, it turns out that it's much more efficient to transmit energy or power in the form of AC than it is DC. And one of the reasons is that there's a device called a transformer, which we'll talk about. We'll talk about transformers later. But transformers allow us to increase the voltage. And when I increase AC voltage, the current decreases. And when you transmit energy at a high voltage, low current, it's way, way more efficient than doing it, say, with DC. So that's the reason we have both AC and DC. Typically, we use AC to transmit the power or energy. We get the energy or power where we want it. We typically convert it back to DC. And most devices you use are probably DC. You might have something like a vacuum cleaner or refrigerator that's AC, but even if you take your cell phone, you plug it into an AC outlet, or you take a TV set and plug it into an AC outlet, there's actually circuits inside the devices that change the voltage from AC to DC because the machine actually wants DC. So there's both of those, DC and AC. So that's the basic generator. I don't know if you have the handout. Again, it's on Blackboard, but my first bullet note is to talk about the basic generator, the construction of a basic generator. And all you need to know about that is this, that I have, magnets, something to create a magnetic field, and I have a coil, and some kind of way I got to move that coil. And when I move it, I'm rotating the coil in the magnetic field. And when I do that, I have what we call a rotating machine, and that rotating generator will create a current or voltage that alternates back and forth. And so on the handout, it talks about the basic generator construction. This is kind of what I mean. Now, this is a functional diagram. You can't build this like this and have it work. This is just a way to understand how generators work. If you open up a generator, it'll be a little bit more complicated than this. But basically, this is how a generator works. Now, there's some terminology to talk about for a second. And I want to review something from your math class. I'm sure you guys are already familiar with, but we'll review it anyway. So you saw that voltage basically was a sine wave. And if I take this part of the sine waves continue on forever, but that's one cycle. So every time that generator coil goes around one time, it creates a voltage pulse or current pulse or wave that looks like this. We'll put voltage up there for now. I called it current last time, I'm going to call it V for now. So this is volts, and this is time. So when I lost my light. There's a motion detector in here, and if I don't move around, let me see if I can leave the camera frame and get it to come back on. Well, I got to unmic myself now and go over there and move around. I'll be right back. So that's one problem I have. There's a motion detector on the ceiling, and with no students in here, I'm in the middle of a recording session, and because there's no motion, I can't adjust the motion detector on me, and because there's no students in here moving around, the lights die off on me in every session that's happened. But what I was saying was, I want to remind you that when you have a sine wave, a sine function, we can talk about this axis right here on time in seconds. So I can talk about it in seconds, but I can also talk about it in degrees, or I can have a unit called a radian. I just want to review real fast. I'm sure you've seen this in your trig or whenever you had math. But this represents that coil in the generator going around one time, 360 degrees. So if I look at this in degrees, this here is 360. And these are the points these are the important points I want you to know. And then so half of 360 is, of course, 180. And then this is an important point right here. This is 90 degrees. So notice at 90 degrees right here, the voltage is as high as this is going to get. It goes up at 90 degrees, and then it goes back to zero right here. Over here, that's 270 degrees. So at 270, I have what we call a peak value. At 90, I have a maximum value, a peak value. And over here at 270, I have a peak value in the negative direction. And then probably 45 is probably good to know, 45 degrees. So I can have this axis in degrees. Or the radian, if you remember radians, one time around the circle, one revolution is 360 degrees. That's 2 pi radians. I won't go into the definition of a radian, but you guys worked with this before. If not, let me know and I can explain it. But it's a unit, a circular unit. If this is 2 pi radians, then half of this would be pi radians. And half of that would be pi over 2 radians. So 90 degrees is like pi over 2 radians, and half of that is pi over 4 radians. So pi over 4 is like 45 degrees. And I got, this is pi over 2. This is pi. If I take a half of pi and another half of pi, I got pi. So I got 1/2 pi, 2/2 pi. This would be 3/2 pi radians. So one of the things you should be able to do with this stuff is give me this horizontal axis in either degrees or radians. So again, I'll record this, but I'm sure you've seen this stuff before. Now, most of the time we'll work in degrees, but you should be able to go between the two. Now, let me clean this up, and I want to talk about some values. I'm going to list them out on the board, and I want you guys to write this down. So these are AC terms that I want to list and explain with the graph. And I got them written on the sheet, the topic sheet, so I want to go in this order. So one term is peak value. And then we got what we call the peak value. Peak to peak value. And then we got the average value. And then we got the RMS value. And this one actually is pretty important. And I got another one on here called the instantaneous value, but I'll talk about that in just a second. So let's talk about these values and how they relate to the graph that I showed you. So I'm going to put the graph back on the board. And again, I'm going to show one cycle of, this can be voltage again. So this is voltage. And for now, I'm going to put on here degrees. And one cycle was like this. Now, this voltage at 90 degrees, this was 90 degrees. At 90 degrees and at 270 degrees, we got maximum values. And so if I go to 90 degrees, and I go up to this top part and over to the axis right there, that point right there, that's called the peak value. The peak value of the voltage. Now, whatever I say for voltage is also true for current. I can change that to current if I want to, and that would be the peak current. So one value you got to know is the peak value of the current or the peak value of the voltage. And on the graph, you can just literally just read it. Now there's a positive peak, and then over here there's a negative peak. But positive and negative doesn't mean much right now. Just for the peak value, come over here, go across there, and you got the peak value of the voltage. So if I want to show 100 volts peak, I might put a little PK right there so I know it's a peak value. So that's one value, or one, if you were here in the lab with me now, there's a device called an oscilloscope that we can use to make measurements of AC. And we can actually see this sine wave of voltage. You can read off the peak value on the screen if you were here in lab. Well, so the peak value is one important value. the peak-to-peak value is another important value. So instead of measuring from, on the graph, from this point to this point, what we do is we measure from one peak to the other. So if I measure, the positive peak is here and the negative peak is here. If I measure from here to here, from this peak to the bottom of this peak, then I have something called the peak-to-peak value. So let me put some numbers in here. Let's say I had something simple, 100 volts. This was 100 volts. I have a 100-volt peak, but then I got my negative 100 volts down here. So I would have 200 volts. I put up 2 P's right there for peak to peak. And it's the same value. The peak value is half the peak to peak value, but this is just different ways to talk about an AC voltage or to measure an AC voltage. Again, if you were here with me in lab and you look at the device we use to measure the voltage, the oscilloscope, you can measure the peak voltage or you can measure the peak to peak voltage. It doesn't matter which one, it just depends on what we're talking about. So, but you should be able to identify for me on the graph the peak value of a current or voltage and the peak-to-peak value of a current or voltage. There's this thing called the average value. I'll tell you what it is, but we won't really work with this. But the most important one is the RMS value. I'll talk about that in just a second. So when they say the average value, think about what an average is. There's different averages, types of averages. But basically, most people think of an average. Let's say you have 10 students in the class. They all take a test and they get different scores. If I want to find the average or the middle value, what I would do is I would add up all those scores and I would divide by the number of students. So add up all the scores, divide by 10 in this case. And the value I get is kind of the middle value. That's what often we think of average, that's what we mean. Well, if I did that with a sine wave, we got a problem because between 0 degrees and 180, I got all these values that are positive. And between 180 and 360, I got the same exact values, but they're all negative. So if I add up positive values that are the same as negative values, when I add them together, I get 0. So what I'm saying is the average of a sine wave is 0 if I go from 0 degrees all the way out to 360. So when we talk about the average value of the sine wave, we don't talk about the full cycle. We only talk about half of it. So this average is the half cycle average. And you can get that by, let's call this V average. V average, I'll write it that way. But you can get that by taking 0.637 times the peak value. So if I give you the peak value, you can multiply by 0.637, and that'll give you the average value. So the average value of the half cycle might be down here like this. Well, let's say it like this. If this was 10 volts peak, then if I take this and multiply by 10, then the average value is down here at 6.37 volts. That would be the average value for half a cycle. And again, we don't really, well, I won't say we don't use it. You guys won't use it for what we do in class. I just want you to know what it is. It's a half cycle average and how you would get it. What is important though is this RMS. I want to get rid of this other stuff and talk about RMS because that's pretty important. So RMS, it stands for root mean squared. Root mean squared. RMS. You don't have to know that, but what it is in the formula to get the RMS value, there's a complicated formula that involves a square root. It involves taking the mean, which is a kind of an average. It involves some math basically, and so they kind of named the voltage after some of the mathematical operations you got to do to get it. They call the root mean squared. There's a root, a square root. There's some kind of average you take with some calculus or something, and then there's a square in there. So they call it the RMS value. Another thing they call it that I actually like a little better, they call this the effective value. The effective value. Effective value. And so it turns out that when we talk about AC, in lab, when we measure AC, we can measure the peak value, peak-to-peak value. You can calculate the average value. But the most useful one is this RMS value or effective value. And I want to attempt to show you why it's important. So I'm going to erase this. And I'm going to try to explain to you the meaning of RMS. The meaning of RMS. What does it mean? Not the letters, but physically, when you write down the RMS value, let's say you can have a AC signal that's 120 volts RMS. What exactly does that mean? So I want to talk about that. And the way I'm going to attempt to explain it, and I said attempt, hopefully you understand it, is what a kind of little thought experiment. Imagine that you have a tub of water. I got this pan, and in the pan I have some water. I'll fill it with water. And then I have this circuit. I got 3 parts to a circuit. I have a DC voltage source. I have a switch, so I can turn it off and on. Then I have a resistor, but I'm going to put that resistor in the water. In the pan of water. This is a switch. And then I'm going to stick in the water a thermometer. Here's a thermometer. And the thermometer is at a certain temperature. So the thermometer starts out right there at that temperature. Call it T1 or something. I close the switch. When this switch is closed, current can flow through that resistor, and the resistor is going to heat up. It's going to dissipate power. And when it heats up, let me put a value on this. Let's just say, again, it's 100 volts. So I got 100 volts. When this heats up, the thermometer is going to rise to a certain point. Let's say it goes up to this point right here, and then it stops. So this second point, I'm going to call that T2. As long as I don't change the voltage or the resistance, this thing will keep a temperature on the thermometer up at T2. What I do now is I open up the switch. When I open up the switch, the resistor is going to stop conducting electricity. It's going to cool off, and the thermometer will go back down to where it was before, T1. Now what I do is I remove the battery. Now here's the new thing I have to show you. When I want to talk about a DC source, I can either draw a battery like this, or I can draw it like this. Pretty much they're the same. This is actually a battery. This is a cell. We talked about that. Or I can use this. There's 3 ways to show DC voltage. But AC, when I want to show AC voltage, I draw this circle, but I show a little sine wave in here like this. That's AC. So what I want to do is remove the battery and put some kind of generator in there, some kind of AC generator. So I'm going to show the symbol for AC, something that generates AC. But not only that, I'm going to put a line through it like this. Now, what does a line mean to a symbol like that? Well, if I have a voltage source of 100 volts, that's called a fixed voltage. There's always 100 volts across this thing. But if I show a line through it, what I'm trying to tell you is that this can be varied from 0 to 100 volts. So anything with a line through it means I can vary it. You've seen that with a resistor. I can have a resistor like this. That's a fixed resistor. If I show a line through it like that, that's a resistor whose value I can vary by turning the knob or moving the lever or something. So I'm showing you over here that I have an AC source. I'm going to put that arrow through it. That means I have an AC source whose value I can vary. And what I'm going to do is I'm going to hook that AC source up, take the DC source away. I'm going to close the switch again. But this time what I want to do, turn this down to 0, so it's not at 100 volts right now. I'm going to slowly start to crank this up. And as I start to crank it up, what happens is this resistor is going to get warm and the thermometer is going to go up just a little bit. My goal is to keep turning this up slowly. This is going to heat up a little more. And what I want to do is try to get the thermometer to go up where it was when I had the DC source in there. When I get that to happen, I know that the AC source and the DC source are basically doing the same amount of electrical work. That's kind of a slick way of doing it because I'm not measuring anything electrical over here. I'm just measuring temperature. I'm just measuring the heat in the water. So if I can turn this voltage up and get the thermometer to stop exactly where it was when the DC source was in there, that means the AC source is doing the same amount of electrical work as the DC source. It turns out, if you think about it, just think about what the waves look like, what the graphs look like. If a DC source over time, this is time, and this is DC, it's constant over time, like that. This goes on forever. AC, let's just say this was 100 volts DC, since I had a 100 volt battery in there. AC is doing this. So if I just look at one cycle of this, say I just look in this box right here. I look in that box right there. The DC is doing work all the time. It's doing work in that whole red area there, that whole shaded area. The DC voltage is basically on. The AC voltage is only on for this part and for this part. The point I'm making is if I want the AC to do the same amount of work as the battery, I'm going to have to turn this up more. I got to turn it up and make the AC bigger. One way to think about it is like this. Suppose I had the DC source of 100 volts. So let me make my graph for that, 100 volts over time. So it was 100 volts. And the DC looked like that. Let's just say I looked at that for a certain time t. I don't know what it is. It doesn't really matter. And I looked at 1/2 cycle of the AC for that same amount of time. Like that. So this peak value of the AC, that V peak, is 100 volts. But notice, it's only 100 volts for that much of the cycle. The DC is 100 volts for that whole square. The DC is doing work over here, and all of here. The AC is only doing work for the area under that curve. If you can follow, hopefully guys, you can follow what I'm saying. The point I'm making is this. If I want the AC source to do the same amount of work as the DC source, what I got to do is I got to turn the AC up a little bit higher than 100. And then if I could push it down and smash it down like if it was rubber, I can keep turning it up higher and pushing it down. If I can push it down so that the orange, the AC, fills out the same amount of space or area as the DC, I know that the two sources are doing the same amount of electrical work. Well, it's kind of hard to say all that, but basically, that's what RMS is. If I have a 120 volt RMS signal, what I'm saying is that AC generator or that AC source is doing the same amount of electrical work as a 120 volt DC battery. So it's a way of equating AC to DC. Now that's important because most of the time when you buy a piece of equipment or you deal with AC, you're not going to deal with the peak to peak value or the peak value or the average. You'll see RMS. So most of the time you see a value for AC, we'll just assume it's RMS unless otherwise specified. And the other name is the effective value. So the effective value is just another way for the RMS value. So the effective value of a 120 volt AC source, the effective value, effectively I'm doing the same amount of work as a 120 volt DC battery, if that makes any sense. So that's a little of the theory behind it. Hopefully you can understand it. If not, maybe you can play the video back a few times, you can see it. But even if you don't, I'm not going to ask you for this diagram. I just want you to know how to convert from one voltage type to another. So let me list them on the board again. You got the peak value, which you can just get from a graph. So if I got a graph like this, time, and this could be V or I, you got the graph. And the peak value you can just read from the graph. It's just the highest or the lowest value on the graph. That will be my peak value. Well, given the peak value, you can get the peak to peak value. So the peak to peak value is just 2V peak. So if I know that this is 100 volts peak, then the peak to peak value is just 2 times V peak, or for this it would be 200. So given the peak value, you should be able to calculate the peak to peak value. I gave you the equation for the average value. I'll give it to you again. I think I had a G there. It's 0.637 times the peak value. But the most important one is VRMS. VRMS. And that's equal to 0.707 times the peak value. This is the one I really want you guys to know. This one's the important one. So this is also, you might write yourself a note, this is also called the effective value, V effective. Now, if you look in your book, I try to write everything in terms of V peak. I just think it's easy to remember. You guys got equation sheets and you're doing it at home anyway, so it doesn't matter. You can just look this stuff up. But in your book, or if you look online, they may have a square root of 2 in there. It's the same thing. You can get they'll have 1.41 something or 0.707. It's just the difference of 1 over root 2 or root 2. But if you see the root 2, I don't want you to get confused if you look at some other than what I'm doing. It's the same number. When you take the square root of 1 over the square root of 2 or the square root of 2, you'll get numbers that are similar here. The only thing I didn't mention, I don't know if you guys are looking at the handout, would be the instantaneous value. I'm going to talk about the instantaneous value real quick, and I want to give you 3 other definitions, but I'm not going to ask anything about the instantaneous value. The instantaneous value is just what the name implies. If this axis is given in time, seconds, milliseconds, microseconds, the instantaneous value is this. You pick a time and tell me to look at it, and I'll tell you what the voltage is. For example, at t equals 0, right here, the instantaneous voltage, and usually we write instantaneous values with a lowercase, that's a lowercase b, would be 0 volts. If you tell me to look at it right here, at that time, the instantaneous value is 100 volts. So the instantaneous value can be anything between 0 and 100. It just depends on when I look at it. If I look at it over here, it's a negative value. So the instantaneous value is the value at a certain time, which for us in here is going to be totally useless, but you should know what it is, the instantaneous value. The value of the voltage at a certain time. And the way you'll get that is by looking at a graph. You can get it from an equation or a graph, but you can get that by looking at a graph. I give you a value for t, you tell me what the v is for the corresponding time or t, if I were to ask that, but I won't. Okay, so my light is out again, so I gotta disconnect and go back and move again. I try to adjust that motion detector, but I just can't get it to work right for me. All right, let me see. Okay, so there are 3 more terms I want to talk about, 2 important, and I want to do some problems, give you guys some calculations to do, and then that'll be it. We'll call it, I think I've been going for an hour, but probably about another 15 minutes we'll be done, and we'll call it a day. We won't do anything else other than this, and I'll post some stuff to Blackboard for you guys to work on. Let me talk about 3 other terms. So I want to talk about frequency and period of a wave. The frequency and the period of a wave. Now, if you're looking at the handout, the last thing is the wavelength. I'll talk about that before we end the session, but that's not important for what we're doing, but I do want to mention it. Let's talk about the frequency and the period. Now, the period, let me draw another wave here. The way to think of the period, if this horizontal axis is in time, and this can be in volts or current, volts or amps, doesn't matter. And let's say I have a graph that looks like this, and that just keeps going. Well, the way to think of the period, the thing that's making this sine wave is a generator. As it goes around 360 degrees, it creates a cycle. And it goes around another 360 degrees, creates another cycle. So as the generator rotates, this thing just continues to go on and on and on forever. But if you can take a snapshot of this, and you can measure the time, the time, for one cycle, from there to there. If you can measure the time from there to there, that's what we mean by the period. The period, in other words, we'll say it's the time for one cycle or one complete revolution of the generator. That's the period. The frequency, if you can imagine this thing moving, this sine wave cycle, I'm going to put a box around it, moving down that way, and you're like right here watching it, is the number of those cycles you see go by in a second. So let me erase this. Say I have I call it a time space. I'm gonna look at time, a time on 1 second. I got fixed to a second. All I can measure is how many events happened in a second. That's a time space. So my time space is 1 second. From there to there in time, that's 1 second. From there to there. And what I see in that 1 second is this. Then that's a frequency of 1 cycle per second. If in that time space I see this and then this, well, that's 2 cycles. That green is not showing up. So if I got 2 cycles, that's 2 cycles per second. Or I might have 4 cycles per second. So the frequency is a number of cycles per second. You can see that the more cycles per second, the more those waves are squished together. So if I show you something like this, and I show you something like that, this one's at a lower frequency than that, because this is less cycles per second than that one is. Now, we don't use any more cycles per second. We redefine a cycle per second as 1 hertz. So instead of 2 cycles per second, we will say 2 hertz, capital H, lowercase z. Or in 1 cycle per second, we say 1 hertz. So we'll use that for frequency. The relationship between frequency and period. So frequency, I'll use a F for that. And the period, I'll use a capital T like that. And then the relationship between the two is that the frequency is 1 over period, or period is 1 over the frequency. So those are 2 formulas you want to write down and make sure you know. This one and that one. Okay? Now, if you're using this formula, just let me point this out. If period, well, let me do it like this. If frequency is 1 over the period, well, the period is a unit of time, usually seconds. So the unit would be seconds. So frequency, this would be 1 over seconds, if seconds is on the bottom. That means that frequency has a unit of seconds to the -1. Now, how did I get -1? Well, you remember in your math class, if I have 1 over a to the n, I can bring that up and put it in the numerator if I make the n negative. So that's what I did. If I have 1 over time in seconds, if I do the division and bring that up, that's what I call an inverse second. Well, 1 hertz is equivalent to an inverse second. So that's another way to think of it, an inverse second or 1 over seconds. So the last thing is the other term on the handout. H is called the wavelength. I want to mention that just briefly, the wavelength. And without too much explanation, the wavelength, if I have a sine wave, and this could actually be meters. So that horizontal axis could be degrees, it can be radians, it can be seconds, it can also be meters. And if it were in meters, and my sine wave looked like this, just kept going, the wavelength, one way to measure it is I go for 1 whole cycle, and I measure not the length of the actual wave, but the shadow that it would cast on this axis right here. So the wavelength would be from here all the way over to here. That's what I mean by the wavelength. They use, it looks like an upside down Y. That's the lambda. That's the Greek letter lambda for wavelength. And the unit would be the meters. So I can have a wavelength that's 100 meters. Not important for anything we're doing in this class, but this actually has some application if you were to take a electronics communication class or radio waves or those kind of electromagnetic waves, then this will be important. I just want to mention it. We won't ever use it in this class, but if you take a physics or optics or something like this, then that'll come up. So we're almost done. I just want to show you how we would represent the instantaneous value of an AC waveform mathematically, and then I want to do a couple calculations. I don't know if you have the handout or not. I'm going to write what I have on the handout. These would be the practice problems if you were here in class. What I have is this sine theta. So let me talk about this equation and what it means and how to use it. So this right here represents the instantaneous voltage. This right here represents the peak voltage. Now I'm saying voltage, but I can have an I here and a capital IP here, and that would be the instantaneous current. This would be the peak current. Whatever I'm saying for voltage, you can take out the V and put an I there. Whatever I say for voltage is also true for current. And this theta represents an angle. And usually you're given the angle and the peak value, you can tell me what the instantaneous voltage is. So remember I said that axis, when you have that axis, I can have degrees, radians, meters. Well, if this was in degrees, and I gave you a sine wave, I can tell you give me the value at 90 degrees. You can put that in there and you can tell me what the instantaneous value is at 90 degrees or whatever the position is. So let me give you the problem I actually have on the paper and you'll see what I'm saying. So the way you might see the instantaneous voltage is like this. The problem is the instantaneous voltage is equal to 167.5 sine theta. And what they want you to find, given this expression, they want you to find a couple things. They want you to find the peak value. So find the peak value. Find the peak-to-peak value. They want you to find the RMS value. And they want you to find the average value. So you guys, if you have a calculator, I'll give you a second if you're following me still, if you're still out there. Get your calculator and a piece of paper and calculate those values for me. And then that'll be it. We'll call it a day. So I'm gonna give you a second to get your calculator and to do this. And I'm gonna run and get my calculator. I'll leave the screen for a minute. Okay, so I don't know who that was. Let me see if I could. My message just popped away. But somebody said I was missing some values. The only thing that you can't find here, because if you remember, let me put this up. This will make more sense. The instantaneous voltage is equal to, this is the peak value. And this is the sine of the angle. So just by looking at this equation, you can get this value right here, right? That would be the peak value. The only time you need to know the question was, how can I calculate anything when I'm missing variables? I don't know this or that. Well, because we know those equations, really, for those equations over there, all I need is the peak value. So given that, now if I wanted to know this, then I would have to know theta. I have to give you an angle. But this peak value, you can just look at that and say, all right, I know what that is. Peak value is just that. It's 167.5 volts. So given this equation, you can just look at the number in front of the sign, and that is your peak value. So given that, these are all based on the peak value, so you should be able to calculate those. So if you got a calculator, go ahead and calculate those real quick. I guess I can use the calculator on here. Let me see if that'll work. Okay, so we got the peak value by inspection, by just looking at it. The peak value is just twice the peak value. So I gotta take this and multiply by 2. And if you take 167.5 and you multiply that by 2, I get 335 volts. This is a peak value. This would be the peak to peak value. And then they want the RMS value. Well, to get that, you just take 0.707 times the peak value. So if I take 0.707 times the peak value, 0.707 times 167.5, I get about 118 volts RM. That's a terrible 8. So I get 118 volts RMS. Now that's important. What does that mean? Well, it means that this generator, when it generates that voltage of 167.5 volts peak, it's doing the same amount of electrical work as a 118 volt battery. That's the effective value or the RMS value. This equates it to DC, which makes it very, very important. And then the last calculation, if I want to find the average value, is just 0.637 times the peak value. So all of these are done in terms of the peak value. And I did that on purpose because I knew I would give you something like this and want you to be able to find those values. Again, the most important one is the RMS value. So let's finish this out. 0.637 times 167.5, I got about 107. So this is 107 volts average. So I don't know how I'm going to test you guys. I don't know right now. I got to figure this out. We're doing this remote stuff. But whatever it is, you need to be able to do a basic calculation like this. Now, I'm getting some kind of message here. Okay. Next time we get together, we'll come in and I'll give you, I'll show you how to use this part of it to get the instantaneous voltage. But most of the time we do calculations is going to be the RMS value. So I'll figure out how I'm going to quiz and test you guys, but I want you to just study this stuff right here and be able to do that for next week. Here's what I'm going to do, a couple things. I'm going to, not today, but tomorrow, I'm going to post, I've already posted the topic sheet. I'm going to tie it to this video I'm making right now. I'm going to post some practice problems with solutions for you to practice this kind of stuff. And then next week, I'm going to have to move the syllabus around a little bit, but we'll do some more calculations. The lab. The way we're going to handle the lab, I don't know if I mentioned this at the beginning. There's a simulation software called Multisim. It's kind of expensive, but we got a license where you can download it for free through June. So I'll give you, what I'm going to do is scan the document and put it up on Blackboard. What it is the instructions on where to go and how to download the software. So you'll go download the software, and on the instructions I give you, there'll be a code. You can enter that code, and then you can use the software for free all the way through the beginning or end of June. It'll take you through the semester. That's what's important. And we'll do our labs like that. We'll do them. You'll do virtual labs. We won't do one tonight, but I'll post a lab up. There's one. I'll post a couple things up. I'll give you the information to download the software. I'm going to give you a tutorial. I'll post that up tomorrow. What I want you to do is download the software and go through the tutorial a couple times to get familiar with it. Then I'll also post a practice lab, not a practice lab. It's a lab to take you through the software so I know that you understand it. I'm going to give you credits, full-blown lab with a grade. Once you go through that, then we'll continue working from the handouts that I've been passing out. So that means nothing else tonight. I'm going to end this here in just a second. But tomorrow, I'll put this video up on Blackboard. I'll attach the topic sheet to it. The topic sheet's on Blackboard now, but I'll attach it to the video. I'll attach some practice problems with solutions, homework, and I'll give you a tutorial on how to use Multisim, and I'll give you a sheet on how to download it with the code that you can use to download it. Now, I know you can download it to a PC. I don't know how it works with Mac. If you have a Mac or Apple, try it. If you have any issues, let me know, and there's other ways around it. I can tell you other ways you can use the software, but if you have a PC, you should be able to download it with no problem. So that's it. If you guys have any questions for me, if you don't, we'll end this for now, and I will send out a link next week around the same time, 6 o'clock. We'll do more of this, and I'll give you the information for lab tomorrow, and then we'll have another lab next week. Now, as far as how I'm going to collect the material, I don't know yet. So you just do the work and keep the work, and I'll figure out how we're going to collect it. I don't know if I want to have you guys turn it in, or I have over 100 students this semester, so there's no way I can have everybody scanning stuff and uploading it to Blackboard. That's not going to work for me. So we'll work something out, but you just do the assignment, keep up with it, and I'll figure the other stuff out later. So you guys have a great rest of the day. Stay safe, and I'll see you the same time, same place next week. If you have any questions for me, I will be here during my office hours on the syllabus, and any scheduled class that I have, I'll be here for those classes making videos. So if for some reason you have to come up or you want to call me, I'm available. Just let me know. So if you guys don't have any questions, you have a great rest of the day, and I'm going to end the recording session now. Thank you.